Alright, so derivatives, tangents, and revenue. Basically, the first one is just find the equation of the tangent line to f of x equals blah at some point. So when it's asking for the tangent line, what it's wanting is some same slope or velocity at some point, basically, right? So if we have an equation of a tangent line, well, it's equation of a line, so we have y equals some slope, x minus some point, plus another point, right? x1, y1. M here is going to be the slope or the velocity. So by the definition of the tangent, if we want the same slope or the velocity, right, it's basically just like barely touches. So if you have some function like this, so you have like x equals a here, you want to align such that it like barely scrapes by, right? So what we can do is we know that the derivative is going to give us the velocity at some point, right? So we can use that to find the same slope. So take the derivative of our f at x function. We do that by the power rule, which is basically just if we have ax to the n, well, we bring the power down. Bring it down here. That's why they call it the power rule. Times a, the coefficient, to the x to the n minus 1, right? So we subtract 1. And we're just going to continue this process over and over again. Right, so what would the next one be? Well, the next one is just going to be na, to bring it down, n minus 1, to the x, to the n minus 1, minus 1, right? You're just going to repeat that process. Okay, so after doing the power rule, we get this function over here. We specifically wanted it such that it had the same slope at 2, right? So we're going to put that point in. F prime of 2 is equal to 2 times 2 plus 2, which is just 6. So this is the velocity of the function at 2. So we know that the tangent is going to want the same slope, so we're just going to put that into the equation of our tangent line. We have x1 and we have y1, 2 and 4, so put those in, x minus 2 plus 4, and we have the same slope, 6, right? Distribute that out, simplify, we get the equation of the tangent line is 6x minus 8. Right, so if we wanted to check that, we actually could. Right, so we know that if it's just going to be barely scrape by or intersect at that specific point, then what is that going to be? Well, then we should have that f at x minus y. A solution to that's going to be x equals that point, or x equals 2. Right? It's just going to intersect at that point, right here. So we can check that f at x equals y. Set them equal to each other. Move everything over to solve. We simplify over here. We notice we can factor this, x minus 2 squared. So if we were to set that equal to 0, well, what would we get? X minus 2 squared, that's just going to be x minus 2, which goes to x equals 2, which is exactly what we wanted. So this basically verifies that it has the same slope. They intersect at that point. And we use the part over on the left to find that they have the same slope. Okay. And that's just the graph I drew here to visualize what's happening. The equation of the tangent line, we have x equals 2, just goes into it right there. Okay, what's 2? A company manufactures and sells X products per week. If the weekly cost and revenue equations are, this is going to be our cost, right? C for cost, R for revenue. These functions blah over this domain. Find the marginal revenue and marginal profit when the number of product is 2,000 units per week. So the marginal of something is going to be the derivative of that thing. So marginal revenue is going to be the derivative of the revenue. Profit is just going to be the revenue minus the cost. So in that case, the marginal profit, if we were to take the derivative of both sides, is just going to be the derivative of the profit equals the derivative of the revenue minus the derivative of the cost. Right? We just prime both sides. So A is asking for the marginal revenue. Well, we're just going to take the derivative of our revenue function. We see that we can do that by the power rule. So we have x to the 1. That's just going to go to, well, it's just going to disappear. So we're going to be left with a constant 10. We have minus x squared. Bring the 2 down. Minus 1. That's going to go to 2x over 1,000. Notice that we can divide 2 into 1,000. So we have 500. So that's just the revenue function, the marginal. B is the marginal profit when the number of product is 2,000 units per week. So we're going to sub that in after we find it. since we know that the profit is just revenue minus cost, the marginal profit is just going to be the marginal revenue minus the marginal cost, which is going to be the derivative. So we find the derivative of the cost. We see that that just goes to 2 because the constant disappears. 2x to the 1 is just 2. Get this. We notice we can simplify this piece, collect them. 8 minus x over 500. So the last step is to find it when the product is 2,000 units per week. So we sub that in. 8 minus 2,000 over 500. That's just going to go to 4. So we have 8 minus 4, which goes to 4. That's basically for that. The derivative of the following functions. So the first function is going to be use the quotient rule. You could technically use the product rule. You could rewrite the function like this. Right? Use the product rule and the chain rule and the power rule. And yeah, it's just a mess. I wouldn't do that. I wouldn't do it this way. Yeah, so we're going to use the quotient rule, which is basically just if we have a function on the top and bottom, I'm going to take the derivative of the top times it by the bottom, subtract that by the top times the derivative of the bottom, and then all of that over the bottom squared, right? So we're just going to write that out. Derivative top, bottom, derivative, bottom squared. This is just going to require the power rule, right? This is also just the power rule. So you could technically stop here if it didn't ask you to go any further, right here. If it asks you to simplify though, right, you're just going to distribute it in. After we do that, we're going to want to see if we can collect like terms. We see that we can, right? This is x to the 3, this is x to the 3. In order to do that, you may have to equate denominators. I wrote it over here. So you had like 1 over a plus 1 over b. Well, that just goes to cross multiply, equate denominators, which is just b plus a over ab. So I did that here for our, imagine this is a, this is our b, this is our c. So I equated all of that, and then I collected them all, right? This would go to 4, this would go to 1, right? So that would just go to 3. What I also noticed is that we had, after doing that, we had 12x minus 3 of this, so we could factor out a 3, which is what I did here. And after doing that, we noticed that a over b over c, in the case where we have brackets on the top, that just goes to a over b c. So after factoring out, we get our 3 here, we have our c here, and this is the result. Okay, so what's the next one? G of x equals f of x, g of x. This is going to use the product rule. Basically, if we have a function times another one, we can say that the derivative of that is just going to go to the derivative of the first times the second, plus the first times the derivative of the second. So this is just some more power rule, right? I wrote it out. This is the first, this is the second, derivative. Find the result, distribute that in. We find that just using the power rule, we get these pieces. Once again, if it didn't ask you to go any further, you could stop here. That is completely fine. In the case it wants you to simplify, just distribute out it once more. This goes here, this goes here, this goes into this, this goes into this. I highlighted the like terms so we could collect them more easily. 6 and 9, that's 15. 12, 6. Right, that's just going to go to 18 here. 3 and 9, 12. 12. And 6 and 6, 12. Yeah, that's just a big mess to look at, but that's basically it for that. Da, da, da. Okay, let me make sure everything's good first. That's good, that's good, that's good, that's good, that's good. Okay, everything's good. Alright, what's the last one here? Just a bunch of derivatives. So I did write out some rules that you're going to want to know. If we have the derivative of the log base a for some function, basically just the derivative of the function over the function times the natural log of the base, right? And since we're dealing with the natural log, I wrote out, you can imagine the natural log is just log base e, right? I also wrote out that if we have a y equals log base a of b, that just goes to a to the y equals b. Right, we're going to do something with that later. But yeah, since we have another function over another one, right, f of x over g of x, we can use the quotient rule here. Again, you could bring it up, use the product rule, and then the chain rule, and the power rule, and then log rules, and yeah, that's just a mess. I wouldn't do that. So use the quotient rule. So we have the first, the top, the bottom, derivative, squared. And then we're going to want to distribute that in, take the result. So I did that here. Get 1 over x to the ln e, right? We're using our little log piece over here. Times the bottom minus the top times the derivative of the bottom squared. So here's where I use the log piece. Since we have y equals log base a b goes to a y equals b. We can rewrite that as ln e. Since it's log base e, we'll just go to e to the x equals e. If we solve for that, we get x equals 1. Therefore, 1 over x to the ln e, that's just going to go to 1 over x times 1. It's just 1 over x, right? That's why I drew a line here. But yeah, so we get this. Once again, we're going to equate denominators, right? We're going to collect like terms. We have a 4 and a -12. That's just going to go to -8. We have a 3 over x. We can imagine this is our a over b again, right? So if we want to equate like the denominators, we're going to have to multiply everything on the top by our x. So I did that to get to this result. And after that, collect like terms. We already did that. Everything's done. Bring the x down, and that's the final result for that. Let me make sure everything's good here again. Yeah, everything's good there. Okay. B, you can use the quotient rule of the product, whatever you want. But there's a little trick we can do here. We can use the change of base. Basically, if we have log base a, b, we can rewrite that as log base c, b over log base c, a, right? We're just maintaining equivalence. So this, if you rewrite it, if you have any opportunity, like a log over another log, I would rewrite it. It can save you a ton of time. I looked at the solution online calculators would give you, and they're just, I don't know, they're like 5 times long. No, like 8 times longer or something. It's just ridiculous, right? Don't listen to the calculators all the time. Yeah. So you have log 3x over log 2x. We can just rewrite that as log 3x over log 3x over log 3(2). So the log 3x's are going to cancel. What that's going to give us, well, we have a over b over c. This is very different. I'm just going to write that out. B over c. That's going to be a c over b. And since a and b here in this context cancel, we're just going to be left with c, which is log 3 to the 2, log 3(2). Now we notice that log 3(2), well, that's not a function. It's not determinate of anything or dependent on anything. That's just a constant, right? That's a constant. So we take the derivative of a constant. That's just going to go to 0. So here are our final results. Y prime is just 0. Right? If you did the quotient rule, you would have been left with a giant mess. So if you ever have the opportunity, I would do this. Let's see. Y equals 2 to the x, e to the x. Here I would also take the opportunity to, if you can, factor. If you don't factor, you're going to be left with multiple pieces, potentially, depending on what you do, which just gives you more work. But yeah, so I factored it out. Here, since we have some base to the power of x, we can just take the natural log of both sides. I would do that because if you don't, you're going to be left, if you take log, you're going to be left with this result over here, right? You're going to be left with ln of that base that you chose, right? So if we choose to take the natural log of both sides, we get rid of this piece here, right? We don't have to deal with that, which is just much nicer. So natural log both sides. We see that if we take the derivative of both sides, we're going to factor out the constant, just get left with x. The derivative of x is just going to go to 1. since we're taking the derivative with respect to x here, and we have a y, that's just going to leave us with a y prime, right? So here we get y prime over y, because it's the derivative of the inside, remember, f prime of x over f at x. So that goes to y prime over y for ln y. And since it's with respect to x, but we have a y, we do that little y prime notation. So that equals the natural log of 2e, because our x just goes to 1. Then what we can do here is we can multiply our y over y on both sides. That gives us y. Those cancel out. So we get y prime is equal to y ln 2e. We notice that we originally started with y equals 2 to the x, e to the x. So we can just sub that back in. So then we get y prime equals bracket 2e to the x ln bracket 2e. You can just leave your answer here if you want. But we can also use the property that ln ab is equal to ln a plus ln b to split this up into ln 2 plus ln e. And as we talked about earlier, ln e is just 1. So we finally get y prime is equal to bracket 2e to the x bracket ln 2 plus 1. Yeah. That's what we get.